Hello, this is the second integrity video on continuous measurement systems analysis. Prior to watching this video, you should have watched the Part 1 integrity video. You should have watched the YouTube video, which has a nice overview and review of MSA and gauge R&R. And if you need a refresher, you should have also watched the YouTube video that I assigned on the normal distribution. If you're comfortable with the normal distribution, you don't need to watch it, but it is a nice explanation of the normal and how the normal distribution is used in many areas that we'll study going forward on continuous improvement. Well, remember in the previous video we talked about measurement systems analysis. I'll ask again, you can watch the video, and in that we talked about gauge R&R, repeatability and reproducibility. We talked about setting up a gauge R&R study and what's involved in it. And remember, repeatability is the variation that occurs when you repeatedly measure the same unit under exactly the same conditions. You can consider this a fundamental measure of noise. Reproducibility is the variation that occurs when you measure the same unit with the same gauge but have multiple technicians, and or you could be measuring the same part with multiple operators, appraisers, technicians, those terms are all used, and multiple gauges. In gauge R&R, there's typically one gauge, so reproducibility is just appraiser to appraiser or operator variation. And then finally, the total gauge error, the total noise in the measurements due to the measurement system, is sometimes called the total gauge R&R error. And for the gauge study we showed, where they were taking measurements of these metal fittings that go on to a safety valve, you can see in our picture that we had the estimated repeatability of about 19 thousandths of an inch, reproducibility almost 26 thousandths, and then the total gauge R&R was about 32 thousandths. Okay, so let's just go forward a little bit and talk about what we mean by the total error. So remember, for a normal distribution, 6 standard deviations represents 99.73% of all possible observations. So in our case, notice that if we had say a true measurement, in other words, let's circle that, that's the actual dimension of the unit or whatever physical property we're measuring. But notice that even though that's the true measurement, the actual measurement itself can vary by as much as 19.25 thousandths. Okay, that amounts to plus or minus 3 standard deviations of the mean. Okay, so 9.628 amounts to 3 sigma, where this sigma is repeatability. And likewise, the other dimension is minus 3 sigma. So the total variation taken up just by repeatability, the fundamental noise in the measurement system, is almost 20 thousandths or 32% of the tolerance range for the part. Reproducibility, okay, was the variation that occurred, okay, by multiple operators or appraisers measuring the same part with the same gauge. And notice this variation amounts to a total of almost 26 thousandths. Again, this would be, for instance, minus 3 sigma, but in this case it's reproducibility. I'll just abbreviate it, or plus 3 sigma reproducibility. Okay. In other words, even though the true dimension, we have some true dimension for the part, the total variation in the measured dimension, not the true dimension necessarily, the whole dimension is almost 43% of the specification range. And then finally, the total gauge error altogether is about plus or minus 16 thousandths. So even though there is some, say, true value, true dimension of the part, due to all the measurement error, it could vary plus or minus 16 thousandths, whenever that true range might be, and that's almost 54% of the spec range. So a good deal of your range of specification is taken up by measurement error. And on slide 44, we just express this as showing the total spec range is 60 thousandths, and of that, 32 thousandths, a little over that, is taken up by measurement error. Because of this, it's entirely possible for parts that are in specification to be measured out of specification. In other words, we might reject good parts. On the other hand, because of all the measurement error, it's entirely possible that parts that are out of specification could actually be measured as in, even though the parts actually would not be useful in practice. So in this case, we would not consider this gauge capable because of the large amount of variation compared to the specification range. Typically, and this is not a hard and fast rule, should not be viewed that way, we prefer that at a maximum of, say, 30% of the spec range should be taken up by measurement error, although that in no way should be viewed as an absolute. It's a general guideline. Okay. And then finally, now on slide 46, we talked about what's called the precision to tolerance ratio, or P to T. What this is just a comparison of the total measurement error to the specification range. So in our case, the P to T ratio is about 53.5%. In other words, it's just saying, assuming that the measurement error is normally distributed, how much of one normal distribution, how much of the spec range is taken up by one normal distribution of measurement error. And the answer is a little over half the spec range, which is considered pretty high for quality purposes. And I wanted to talk about one last subject, and this is called variance components. This is a general topic in statistics. Our goal here isn't to get into deep discussion of it. In statistics, a variance component is simply some source of noise or random variation in a physical system or process. So in a measurement system, a variance component would be a source of random variation, or we often just call it noise. So the variance components in gauge R&R are reproducibility and repeatability, and possibly part-to-part variation, which is not of direct interest in a measurement study. But variance components in general apply to very complex and large-scale situations where there can be many components. Here we're only talking really about two, but in practice there could be even dozens of them, although that would be on the extreme side. And JUMP does variance components analysis. Basically, it's just figuring out what are all the sources of noise in the system, and then measuring basically their variances or standard deviations. In other words, how much variation do we observe in our output due to each of the components? So gauge R&R is done in variability chart in JMP. In other words, where we did the MSA that we showed in recording number 1. Okay. So we won't get into estimation of variance components. In fact, it turns out variance component estimation is a relatively complicated subject in statistics, and there's a lot of theory around it. Fortunately, again, these days we're using software that makes gauge R&R and variance components analysis relatively simple. But in general, I think variance components are very important in general in studying continuous improvement, because they help us quantify where the major sources of variation may exist in a process. So I'm going to go back to JMP. Okay. And I'm going to move over to the JMP software. Okay. And I'll reopen the gauge 2 data. Okay, remember, this is the gauge R&R study. So we go to Analyze, Quality and Process, and we're going to use the platform Variability/Attribute Gauge Chart. Okay, so remember, the readings are the diameters, that's the response. The groupings, we group the readings by operator, and then JMP gives you a box in which to identify the parts or whatever the samples are, and you need an ID for each of the samples. So we'll put that in part, and reading number is actually not of any value to us in this case. Click OK, and you remember from last time, I'm going to expand out the view a little bit. Okay, and of course we have our standard deviation chart, which could also be called a repeatability chart, since the standard deviations are measuring repeatability of the 2 measurements taken on each part. And we like to use the option connect cell means for the visual effect, and I like to show the group means. So last time we did the gauge R&R, so we go down to gauge studies, and we're going to do gauge R&R. It's crossed, meaning all operators measured all parts. Okay. Remember, the multiplier is 6 because the normal distribution is typically defined as a 6 standard deviation spread, covers 99.73% of a normal distribution, and our tolerance range is 60 thousandths. Click OK, and notice that we're given the study variation, which is 6 times the standard deviation for each of the variance components. Okay. So we have the repeatability component, the reproducibility component, which can be further divided up into operator and operator by part. And we have part variation and total gauge variation. So remember, the key point, when you add up all of the measurement variation, the P to T ratio was 0.54 roughly. In other words, the noise in the measurements alone takes up 54% of the specification range. Well, there's another option available, and I recommend you use it as a part of a gauge R&R, and this is called variance components. Okay. We're going to close, notice the report that says analysis of variance. That's really not of direct use to us here. So I'm going to click the disclosure icon and close it. It doesn't really add anything to what I'm doing. So notice it says the operator variance is 0.912, and that's thousandths squared. And that's literally 0.15% of the total variation. And by the way, the standard deviation due to operator is 0.95 or 96. Part variation is, again, the biggest chunk of variation, takes up 95%. It's not of direct interest to us. But the variance components analysis in gauge R&R can break it out separately, and we're not really using it for anything here, but it's a big part of the variation, but it should be because we picked the parts to be very different. And then finally, the within variation, within variation, this is repeatability. So JMP calls it within. It's literally repeatability, and its standard deviation is 3.2. Okay, so you keep that in mind. Okay, so where do we get the study variation of 19.2? Well, the standard deviation, in other words, the typical repeatability variation in a single measurement, is about 3.2 thousandths. Multiply it by 6 and you get what is often called the study variation. Similarly, for reproducibility, you'd take the total of the operator and operator by part variation, multiply it by 6, okay, and so forth. So that's where we get the idea of the study variation. It comes by taking these standard deviations and multiplying them by 6 and then comparing that to the specification range. Okay. So variance components are very useful because they give you a breakdown in variation, and they show you the relative contributions each has to the total variation. Okay. So I'm going to go back to the notes at this point. And that just showed you how to estimate the variance components. And on slide 55, you see a discussion of them. I've already explained them. Again, we won't get into the estimation of them. There are actually a number of approaches, and it gets into some fairly esoteric theory that really isn't necessary at this level of discussion. Okay, so there are our variance components, the variances, and then the square root or standard deviations, and the percent of the total variation. Okay. So the total measurement system variance, okay, is the sum of the three components. Again, this is a part. This is not including part variation because we're only studying the measurement system. So we add it up, and the total variance, in other words, we add up the variances, is 28.65 for the measurement system. Okay, this is an important point. You can add up the variances. They add up. Standard deviations do not. So we don't add up standard deviations. We add up the variances. They sum to 28.65. So that's the total measurement variance. Take the square root. Oops, that went where I didn't want it to. That's 5.35. Multiply it by 6, and guess what? You get 32.115 thousandths. And that just happened to have been the total gauge error. So we're just showing that actually the traditional gauge R&R report was actually in the background using variance components, but we didn't explicitly show them earlier. But in general, just looking at the variance components alone can be helpful in trying to figure out where you need to focus if a measurement system needs to be improved. Okay. And then basically there's another quick issue to discuss, and that is, if we're going to do a gauge study, how do we select the units or parts? One theory says take a random sample of whatever's available. This is often a recommendation. The other says no, you should pick the samples so they cover the maximum range of variability you would expect to see in practice. The second approach is the one that I most strongly endorse. A random sample really doesn't do anything for you here. These studies are very small, so it's not going to really allow you to study process variation and get a good estimate of it. Again, in our case, the parts or the samples are really not our focus anyway. We're focused on the measurement system. So I'd like to get a wide range of samples in terms of their physical characteristic, like I want a wide range of part diameters. And that allows me to see how the measurement system behaves over the range. And if we have standards, it even allows us to measure linearity. Okay. So basically, I recommend the second approach, and many people that do MSAs also recommend pick a range that covers the actual range of variation you would expect to actually see in practice. Okay. So basically, we've summarized in these two videos the ideas of MSA. There's more to it. This is a subset of what is necessarily a very large topic. Again, textbooks are written, in fact, textbooks are written sometimes on just areas of MSA, not even MSA itself. But we've covered the basics, and these basic approaches like gauge R&R and variance components are quite useful, and in many cases may be sufficient for your uses. Okay, so at this point I'm going to end the video, and this ends the discussion of continuous MSA.